Okay, today we're going to be looking at the lab conservation of angular momentum. So in this lab we have two rotating platters as shown in this diagram here. The top one we're going to call I2. I represents the moment of inertia. And the bottom one we're going to call I1. And that's what our goal in this experiment is, to determine the moment of inertia of the bottom platter, which has these pulleys on it. So I1 is the goal. So let's take a look at the setup. Okay, so here we have this rotating platter. Here's I1 with the pulleys on it. So that one will be on the bottom. And we have another one, I2, which is the top. Okay, so on this first part of the experiment, we're going to have a completely inelastic collision. So this is going to be spinning, and we're going to try to drop this on there a lot more smoothly than that, hopefully. We'll collect some data here in a moment. So that's going to be the basis of the first part of the experiment. The second part of the experiment, we're going to calculate torque, and that's just going to be with these rotating, and torque is going to be due to friction in the bearings, and we should see this slow down due to a frictional torque. So we're going to do the experiment of just it slowing down, and then we're going to repeat that part of the experiment on part B with both of them spinning. Okay? So back to part A. The first part of the experiment is with the collision. So it's a completely inelastic collision, which means the two objects stick together after the collision. So this lab's called conservation of angular momentum, and that's what we have written here. For an isolated system, the angular momentum is conserved. That is, L initial must equal L final, as long as there's no external forces acting on the system. So in this case, we're going to just assume that's true in this experiment. Now, how true is that assumption? Well, that's something that can be discussed and that you will have to determine. So we can break this equation up into L1 initial plus L2 initial. That's the top platter, or the bottom platter and the top platter. The sum of their momentums together must equal the sum of their momentums after the collision. So we can write momentum. Momentum, we have linear momentum, which is P equals mass times velocity. Now, for angular, we have something analogous. The moment of inertia is kind of analogous to mass, and here we have angular velocity instead of linear velocity. So we're going to use angular momentum, I omega. So we can rewrite that for each platter, I1 initial times omega 1 initial plus I2 initial and omega 2 initial. Now I1 and I2, these values will be constant because the moment of inertia is based on the mass and the radius. Now these values are fixed. This is a solid object, so therefore its moment inertia is constant. Now we're going to assume I2 is that of a solid cylinder, 1/2 mr squared, or we can measure the radius and the mass to calculate that. I1, since it's not completely a cylinder, it has these pulleys, it has a couple of screws in it, it's not a solid cylinder, so we're going to use conservation of angular momentum to calculate I1. Again, that is our goal. So what you have to do here is you have to make a few assumptions here. What can we say about omega 2 initial? Remember, omega 2 is the top platter. Think about that. And then you're going to have to solve this equation for I1. Now notice I1 is in two parts of the equation, so therefore you're going to have to isolate every term that has I1 on one side of the equal sign, factor and divide. Okay, so be careful on your algebra there. So that's something you'll have to complete in your notebook. So you're going to have some expression for I1 based on I2 and your omega values. I2 is calculated, And omegas we're going to get from logger pro by measuring the time. All right, so we can look at that here. So again, we have our linear velocity and our angular velocity. We're going to use our angular velocity, but we write it like this so we can compare. Linear velocity is dx dt, and angular velocity is d theta dt, where the angle takes the place of the position. So we can calculate angular velocity based on the angle and the gate time, which is going to be read off logger pro. Now this angle is going to be a piece of paper that's sticking out that will hit the photo gate. Okay, so let's go ahead and briefly discuss part B, and then we'll try to do the experiment. So on part B, we're going to calculate the torque due to friction using Newton's second law, the rotational equivalent. I alpha, mass times acceleration, moment of inertia times angular acceleration equals torque. So we should already have our moment of inertia 1 and 2 from the first part of the experiment when we get to this, and now we have to calculate angular acceleration. So we can look at acceleration, the dv dt, and the angular acceleration d omega dt. So to calculate our acceleration, we're going to have to calculate omegas as we did on part A using the angle and the gate time, and we're going to have to find some time interval. So we're going to have to find two values, a final and initial, and a final and initial. And we'll get that on logger pro as well. And we're going to rotate, as I said, with both one platter and then both platters. Okay, so now let's go back to part A again. So part A, we have our logger pro, and we're going to collect data. Now here we have, here we have this card. This is going to be our angle theta, 1/5 radian, so 0.2 radians divided by whatever gate time. Now the gate time is the time it takes this piece of paper to pass through the gate, so for the time it takes to go from here to here. So that's going to be a very small time. Right, so let's go ahead and hit collect, and we're going to spin it. We should see some data starting to come up here. Okay, now we're going to head and drop this one on there. Okay, I dropped the second platter on there. Now let's see what happens to our data. We see the gate time is on the y-axis and our regular time is on the x-axis. So we see our gate times got significantly larger after the collision. So a larger gate time, that's going to mean a smaller velocity. It's slowed down, so it's taking longer to pass through the gate, which means a larger gate time. So that makes sense. So we're going to be able to collect some data from this. So we're going to use this button called Examine. And we want to pick the point just before the collision and the point just after the collision. Notice there's 2 points during the collision. We do not want that. We want just before the collision and just after the collision. So here we can get a gate time just before 0.0097 seconds. And we will take the angle divided by that gate time to give us our angular velocity. Now since they stuck together, so that is the omega initial, and that is for platter 1. So omega 1 initial is going to be 0.2 radians divided by 0.0097 seconds. Okay, and we can do a similar thing for after the collision. Again, the 0.2 radians divided by our gate time, 0.0189 seconds. will give us omega final. Now notice, since they stuck together, the velocity after the collision is the same. So omega 1 final equals omega 2 final. So when you do your equation, you can make an assumption on how you want to denote these. If we said omega 1 final equals omega 2 final. Okay? Alright, so you will repeat that for several trials, calculate I1 and find an average value. And then that I1 we'll use on part B. So this part's pretty easy, I think. So we're going to rotate platter 1, collect, and all we're going to do is just let it slow down due to friction, and we can see the gate times are increasing. That makes sense. Increasing gate time means slowing down of velocity. Okay, so we'll collect some data there. We'll let it go across the whole thing when we do all of our data. So what we're going to do here, we can pick this to be our final position, so we'll use that gate time. So 0.2 radians divided by the gate time, 0.0129 seconds, will be omega final. And we'll do the same thing here for omega initial. So on this omega final, we'll also write down the time. That'll be our, to calculate the acceleration. So here we'll use our gate time to calculate omega initial, and we'll write down the time. And we'll have that time interval. We'll have omega final minus omega initial, and our time intervals that we wrote down to calculate our acceleration. Our angular acceleration times our moment of inertia that we have from the first part will give us our torque. And you will repeat that again with both platters on here, which I won't show you, but you'll repeat it like this. Okay, so that's the basics of this experiment. Be careful on part B, which eye do you use on when both platters are on there, so keep that in mind. All right, so that will conclude the lab conservation of angular momentum. Thank you.